So we're continuing with question 2, and we're kind of looking at the whole question here in one, because remember the idea here is not, okay, so what we do here is we see a 9 and we go prime base. We need to look at, we're given these questions, and more importantly, we're not just given, okay, we're given every different type of question. You're just given question B and you're going, what's our strategy? How do we start? And how do you know which strategy we're pulling on when we've got our toolbox of mathematical... It's too much, isn't it? Okay, I just happen to have the toolbox there. So let's go through it. And that's why I've got all of them on the page here for question 2 to go. Let's look and try and think. What jumps out? And maybe let's guide this in a few ways. Let's look at number of terms. What jumps out in terms of the number of terms given in question A versus the number of terms in question B, C, and D? Well, what jumps out to me is there's one term equals one term, and here we've got two terms. Here we've got two terms. That's one term, cool. Here we've got two terms. So our strategy is going to be different, and whenever we've seen multiple terms, we generally end up doing some sort of factorization. Not always. Question B is going to be different when we look at the next part of what we're asking ourselves. Where are the unknowns? So where's the variable in the different questions? So is the x as the base, like x to the power of 7? Or is the x in the exponent, like 2 to the power of x? Or if it's an m, like in question C, is it in the exponent? So can you see, and I'm just, because I'm already going to go, let's compare where the variable is in the exponent or in the base, in A, B, C, and D. Okay, so if we look at those, we see variables in the exponent. The variables down here is a base. Variables exponent, variables exponent. So that's going to guide us in how we solve these as well. Number of terms, exponents. Okay, then maybe one of the other things is, what about the bases themselves? So in other words, we're not going to look at this one because the base is the variable. There's only one kind of interesting base here. Are the bases the same, or can we make them the same into generally prime bases? So do we just have a bunch of 2's, 2 to the summing, 2 to the summing, 2 to the summing, or do we have 2 to the something and an 8 to the something? In which case we're going to take it down and prime factorize and change that 8 to 2 cubed, 2 to the power of 3, because then you'll have the same basis. So can you work the question so that you've got the same base all the time? So here we go in question A. So just have a look at, can you see the different types of bases? Okay, now I wanted to pause it there to say, sure, maybe you're still going, what's he on about? But I wanted to pause it there so that you had a chance to be forced to grapple with it. So, I'm busy talking and I had it on mute. That was great coughing, right? But nobody's around here for the next like 10 hours or more. And yeah, anyway. So, what is he on about? The bases and things. So the bases here, we've got a 9 and we've got a 1 over 27. But can we change that into the same type of base? Yeah, we can, because we could change the 9 as like 3 squared, and the 27 we could change to a 3 cubed. So it looks like we can manipulate it so we got the same base. Okay, here, well, the x is in the base, so we're going to do a different strategy. Here, okay, all the bases are already 2, 2, and 2, so there's nothing to be done there. This one, it looks like there's a 4, so just like in question A, maybe we should change that to a 2 squared. I mean, if you look up at our previous question, this question 1e, that's what we did. We saw a 4, 2 squared. We saw an 8, 2 cubed. We saw a 16, 3, 2 to the 4. Here, they were already all prime numbers. Okay, and these were different styles of questions because the variables were not in the exponent. Okay, so what we're getting to in all of this, and we're tackling this whole question, which is a bit different to how we've looked at tests before. We go, okay, here we go, and let's solve this. So we can change that same base It's already all 2's. We could change that to 2 squared. And just to preempt when we're going to get to this question, here we're going to change this to 2 squared to the x. That's what this first term is, which is 2 to the 2x. Now, in this one, we're going to have a 2 to the 2x, and we're going to have a 2 to the x. So, yeah, this is like 2 to the x all squared. And this, I'm hinting towards, we're going to change this. We got 3 terms and into a k1, and let's see why. But let's see why when we get to that one, because once we've done the others, maybe it will stick out a bit more, and it's worthwhile doing it in that way. Okay, but we've got a bit of a sense of the types of questions we're going to ask. So, starting with changing this into the same base. So, for this one, if I just change this, we go, that's great stuff. That's 3 squared, and that's to the power of 2x minus 3. And this one, well, it's 1 over 3 cubed. Okay, let's leave it like that. So all we did was we changed the 27 to 3 cubed, and we know our exponent laws, so we'll get 4x minus 6. Remember to multiply the 2 by everything, so that minus 3 becomes minus 6. And now let's think of other things, another strategy in our toolbox to do with exponents. Well, if we can get, so I'm just going to say, maybe let's just ask, what's the other tool where we can change this that's going to make a fundamental difference so that we can solve this equation? What do we need to make the same, really? Okay, and I'm not asking this in the best way of kind of going fill in the gaps, but if we can make the base the same, then we can say, well, the exponents are going to be the same. So that's one of the tools that we think, if we can get something to bases the same, then exponents the same. And we're going to use this quite often, actually, because we're going to end up using it in question E. It's just going to be a bit further down in the question, and we start using it in other ones as well. Okay, so if something's on the bottom, how do we manipulate it? I always kind of do this because how mathematical is it? But what can we do? How can we write this so that it's just 3 to the power of something? What is this something at the top here? Well, it's negative 3. So if it's a positive exponent and it's just one term like this, then it's negative like that. Spaces are the same, exponents are the same, so that's fine. You can solve that. 4x minus 6 equals minus 3, blah, 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 solve x equals whatever it equals. Okay. Then we look at this next one. We go, we started talking about their 2 terms. What are we trying to do? Oh, the exponents are fine, but the base is the variable. Well, if the base is the variable, then what we've generally done is if you've got let's just give you a simple equation. 5x minus 3 equals 17. Well, you would have gone, plus 3, 5x equals 20, divided by 5, x equals 4. Keep that strategy of linear equations in your mind to go, okay, well, let's try and get this so we can just have it x equals something or other. Okay, so plus 16, 2x to the 3 over 2 equals 16. Okay, well, let's divide by 2, so we got x to the 3 over 2 equals 8. That fits in with how we've been solving equations. And from here, then it's, hang on a second. We don't want x to the 3 over 2. We want just x. So over here, you just wanted x. So you went, we're timesing by 5, so let's divide by 5. So in this case, what can we do so that it just goes, x equals? Well, what ideas do you have at this stage? And I'm hoping that you have some ideas, but I don't know where you are in your revision, and that's the point of these. So you're going, well, let's do that to the power of 2 over 3, to the inverse. Because if you raise a power to a power, you multiply. So 2 over 3 times 3 over 2 times 2 over 3, everything would cancel so nicely to give you 1. In other words, x to the 1. Hey, that's what we want. Whatever you do on one side, do on the other. 8 to the 2/3. Well, 8 squared is 64. Cube root of that is 4. Or, where's my calculator? It's not ready to go. Or calculator to do that. Okay, then the one thing just to remember with these. Do you have a second solution? So I'm going to put a question mark here. Do we also say that x equals minus 4? When do you have that second solution? Okay, maybe you were like, okay, I know, or you're like, what? So the second solution we have is if we had an even number on top. Because at the moment what we're going to do is we're going to cube this and then square root it. That's what 3 over 2 means. Another way, by definition, that it's cubed and then square rooted, or square rooted then cubed. But the point is this one on the bottom is kind of going square root, so therefore we don't have a minus 4 because we can't take the square root of a negative number. So we're not going to look at that as a second solution. Okay, so let's just cross that out so that it's there for reference, but we're not doing that in this case. So revise if that's not quite making sense. Opportunity you've pinpointed. Okay, so this one here. We talked about how many terms there were, and we said the variables were in the exponent. So in this case then, well, what can we do? And hint, look back at a question like this one here. We had to simplify question F. And what did we do in this case in F so that we could simplify it? Maybe we can do a similar strategy for this question. Okay. So the strategy there was to what we called split and factorize. So we said, well, let's see if we can factorize. If we can get a 2 to the m out on this side, well, that would be nice because then 2 to the m equals, and we could cancel those 2 to the m's. So we've got 2 to the m times 2 to the 3, that's the split part, plus, so that's that part, and let's go for this part here, plus 2 to the m times 2 to the 1, and the rest of the equation stands, 2 to the m x plus 4. So already one term and nicely factorized, and from here what we're really trying to spot is to go, there's something common, a 2 to the m. Hey look, there's a 2 to the m everywhere, and we're trying to find x, so maybe that will cancel. So that now looks like our common factor. So this was the split. Now we can factorize and go 2 to the m, 2 cubed plus 2 to the 1 equals, and this side stays the same, 2 to the m x plus 4. And great stuff, we can happily divide each side by 2 to the m, and therefore x plus 4 equals whatever this is, say 10, so x equals 6, and we could find our answer, but from there you should be fine. But there's the exponent side of things. How did we know? 2 terms, we factorized, it looked similar to this kind of thing. So try and make these links. This is the beauty of looking at this more holistically, is to go, that one looks similar to this. Okay, square root. So again, I'm going to scroll up and say, look what we did in this one when we had a square root of some number minus a square root plus or minus a square root of another number. We took out our calculator and we said, okay, well, let's try and see if we can use our calculator to simplify this. So if we have our calculator at the ready, what we're saying is, let's just check that it's coming up when we want it. There it is. Okay, excellent. So we've got our things here and we're going, well, we kind of neglected to look at this one earlier because it looked a bit different to the others, but we've got a square root x. Well, we're going to want to do, maybe I should ask you this. We've got square root. So like the square root of x equals 7. What must x be? Well, you'd hopefully say it's 49 because the square root of 49 is 7. In other words, from both sides, you just went, square that side, square that side. Beautiful, and you got there and checked that your answer worked. 49 does work. You didn't get like negative 49. Okay, so let's do the same, but we don't want to square this thing. Can you imagine squaring this? That's going to look messy. That times itself, no, pause. So think back to that first question. Square root 32. We said, well, let's see what we can do. Maybe square root 32 for square root 2. Okay, so square root x equals this part here is 4 square root 2. That's what our calculator is telling us. And then we're going to add, and this second part here, square root 18, just because they're square roots that could be simplified. And your calculator is doing that work for you. And we don't look at how to do that anymore. What a shame. So square root 18, 3 square root 2. And now it jumps out a bit to go, hey, 2 terms. How often is it that we see 2 terms and we go factorize? Not always, but seems to be a good option. So here's our common factor. So I'm going to run through just the next step of this because it might be useful and go, okay, 4 plus 3 equals square root x. And we use our idea here to go, well, let's square both sides so that we can get x. So then square this right-hand side. Simplify what's in the brackets. So we've got 2 times square root 2 times 7. And we're going to square that. That dear old calculator is your friend again, because you can just put this right-hand side into your calculator to get your answer. You've got it on hand. I'm not going to know that you went, oh, square root 2 squared is 2. 7 times 7 is 49, so it's 98. Why not just use the calculator? It's such a nice resource, and we're not testing that as much anyway. So you punch in, you get x equals whatever. It's like 98 or so. Okay. So our last question, this one's a bit more involved, and let's see what we're doing. 4 to the x plus 2 to the x. So we already looked at this and said, well, it seems so close to getting these as all powers of 2. So we got 2 to the 2x equals, not equals, plus 3 times 2 to the x equals 4. Okay, so I'm going to put the equals 4 here for now. Now hopefully we can try and just recognize something like this to go, well, nothing jumps out. We can't, if we split and factorize. So maybe that's something we think in the back of mind. Okay, 2 to the 2x, 2 to the x, we've already split this. There's no 2 to the x times 2 to the x. So what, a 2 to the x you could take out, well, you're still left with variables inside the bracket. So that strategy is not going to work. So we're going to bail on that one and go, what to do? What to say? So what's your idea at this stage? So it's one thing we kind of haven't done so far. What's your idea on solving this? So maybe you're sitting there and sure, I'm going to say, well, let's subtract 4 from both sides. And therefore, this is going to equal 0. And see if that makes it look a little bit clearer. In what cases do we go, oh, equals 0? Well, quadratic equations was when we used this strategy. Now I'm doing the circular logic in some ways because I'm showing you the solution. But so this is the same as, I don't know, actually maybe we could look at this and just go, do you remember the K method? So when we saw 2x and that, we generally used our K method and said let K equal 2 to the x, that part there. That means that we're not going to have anything except k's in this. And the key trick in this, just as a reminder, because if you don't have it then it's worthwhile just reminding you to go, well, this first bit there is k squared. That is the same as 2 to the x squared. Because look, 2 times x is x times 2, same thing. So then you've got k squared plus 3k minus 4 equals 0. Great stuff. Quadratic, factorize, equals 0, k equals that, k equals that. Substitute this, therefore 2 to the x equals something, or 2 to the x equals something. And one of them might have a solution, one might not. Leave that to you. Okay, so I actually just changed tack there a little bit to say, well, just a reminder, this is, we've seen these types of things, you maybe just recognize a little bit, you've looked at your other strategies, but it jumps out there a little bit once you've seen a few. Okay, I know these are taking a while, but kind of take them for what they are. It's a useful way to maybe revise. Now you've put in your 20-30 minutes and gone, sure, feeling a bit better, that stuff's solidified, because we're solidifying this for not just this year, but for next year as well. So all the work that you're putting in at the moment is basically a nice 2-year project, grade 11, 12. This is it. We don't suddenly go back and revise this from scratch next year. This is it, you're really consolidating this. So well done.